Hello there, welcome to section 3 of unit 1, and in this section we'll be looking at vectors. Let's look at the objectives of this section. Objective 1 is to state what scalar and vector quantities are, give examples of scalar and vector quantities, state the differences between vector quantities and scalar quantities, define what a unit vector is, evaluate a unit vector for a given vector, resolve vectors into components, perform vector multiplication, and lastly, we solve some problems with vectors. So scalar and vector quantity. Anytime we define a quantity with only numbers, we define it as a what? A scalar quantity. So scalar quantity has only magnitude and has no direction. Unlike a vector quantity, we define a number with a specified direction and we say it's a vector quantity. So a vector quantity has both magnitude and direction. Example of a scalar quantity is length, area, volume, speed, mass, density, pressure, temperature, energy, and others. An example of a vector quantity is displacement, velocity, acceleration, momentum, force, lift, draft, and weight. In a presentation of a vector, we represent it with an arrow on it, or we can represent it with a bold A. And with the with the magnitude too, we denote it by bringing an absolute at the side of what the A with an arrow on it. Let's look at the properties of a vector, and here we'll be looking at 3 properties. The first property is the equality of vectors. So if 2 vectors A and B are equal if they have the same magnitude and they point in the same direction regardless of the initial position. So here we can say that a vector here drawn 1, 2, and 3 are equal because they are pointing the same direction and they have the same magnitude, and where they start doesn't matter. Property 2, a vector having a direction opposite to that of a vector A but have the same magnitude is given as negative A. So supposedly we have our vector starting from here which ends here, though no matter the position where this one will also start, but if it goes in the opposite way and have the same magnitude, we say is a negative vector of the initial one. The third property is the addition of vectors. Let's look at the diagram that we have here. Supposing we have a vector A starting from here which ends here, and we have a vector B also starting at the head of the arrow of A and also ending here. Anytime we want to find the resultant vector of A and B, it's from the initial point where the A started to the head of vector B. What is a null vector? A null vector is a vector that has 0 magnitude and no direction. So in case we have vector A is equal to vector B and we say vector A is minus B, then we can represent the B with A, because you know that A is already equal to B. After doing the presentation, when you subtract the 2, we are going to get 0. So here we are having a null vector here. Let's look at the component of a vector. Supposing we are given a couple of vectors and we are asked to find the resultant, we are going to use this formula to help us go about it. So we have a vector starting from here which ends here, but our vector x start from here on the x direction and ends here. Let me use a laser pointer to do. Vector ax start from this point, the origin, and ends here. And our vector ay start from the head and ends here. And we know that anytime we are finding the resultant, it's from the start of vector x to the head of vector y. So the question here is, how do we calculate for ax? How do we calculate for ay? And how do we find the resultant? So here we are going to use trig, and from our trig we know that cos theta is always equals to It's always equals to the adjacent over the hypotenuse. So here cos theta here is good. Our adjacent here is this line. When you take a triangle like this, right, and this place is our theta, our angle theta. Ax is our adjacent, ay is our opposite, and the A here, the resultant here is the hypotenuse, right? So cos theta here is going to be equal to AX over A. That's the adjacent over what? Hypotenuse. So in making AX the subject, we are going to multiply the A plus the times the what? The cos theta, which is going to give us what? A cos theta. Let's look at AY. But for the AY, we are going to use sin theta. And we know that sin theta is always equal to what? The opposite over the hypotenuse. So in case we have an angle here, our opposite here is what? Is AY. And our what? Adjacent hypotenuse, sorry, is our resultant. So sin theta is always going to give us AY over what? A. And making AY the subject, we multiply A by the sin theta and we get what? A sin theta. Moving on, in case you want to find the resultant, from our old previous knowledge, that's from Pythagoras theory, we know that always, in case you want to find the long line that we have here, it's always going to be the square root of the squared of this line plus the squared of this line, as given here. Lastly, in case you want to find the trig of the theta, that is we want to calculate for only the direction, then we find the what? The tan of the theta, which is always going to give us the what? The adjacent and the opposite over the adjacent, as given as here. So here is tan theta is going to give us what? AY over AX. And one thing that we have to put into consideration or remember is anytime the direction goes here for the AX, we are considering a positive, but anytime it goes here, we should be considering a negative. Likewise for the AY, anytime it goes here, we should be considering a positive. Anytime it goes here, we should be considering a negative. So let's look at a unit vector. A unit vector, as the name suggests, is a vector whose magnitude is exactly what? 1. Or we say what? Is unity. And points in a particular what? Direction. The sole purpose of a unit vector is to point or specify what? A direction. And that's all. These unit vectors are manually perpendicular and is presented as what? I and J. That's I for the x-axis and J for the y-axis, as represented here. So the I and the what? And the J. So given a vector A, let's resort it into its various components. Say the direction of x and the direction of y. And also say given a vector B, we can have the x and we can have the what? And the y. Let's bring in R and find the summation of A and what? And B. For a unit vector, we can add I and J. We can add only for the i's and we can add only for the j's, right? So we know that our A here is AXI plus AJY, which is in this bracket. We also know that the second term B is BXI plus what? BYJ, which is presented in the second term here. We have to group the like terms where this term, the BXI joins the what? The AXI, so that we can bring the unit vector outside the bracket. We can do the same thing for the J, and we can represent our Rx to be equal to AX plus BXI, so that we can also present our Ry to be AY plus BY. I hope you do understand. From here, we can calculate the magnitude of R as what? R squared, the square root of R squared X plus the square root of what? Ry squared. And we already know that our Rx is what? AX plus what? BX. And our Ry is equal to what? AY plus BY. Fast forward, we can also calculate for our direction. That's the tan theta equals Rx and Ry. We already know what Rx represents and also what Ry also presents. And we can easily find the theta by just finding the inverse of the whole term that we have. The tan inverse of the whole term that we have here. Great. Let's look at the multiplication of a vector by a scalar. We are multiplying only a vector by a scalar. So suppose we have a vector A moving into this direction, right? Anytime we want to double the size of this one, let's say we multiply 2 by it, we know that the length of this one is going to be doubled up to here as defined in the second diagram. And in case we negate it, from our properties of vectors, we know that what the direction is going to change. So look at the example that we have here. In case we have a vector A equals what, 3i plus 4j plus 5k. 5 comes in, the k comes in if you are looking at the z direction. So direction x, y, z. So I, j, k. And we are asked to determine what? The vector 4k, 4a. So right now we have a scalar what? 4 and a vector a to be multiplied. So we can just write 4 here and multiply it through the whole vector of what? Of a. So this time around, 4 is going to multiply the 3i, 4 is going to multiply the 4j, and 4 is going to multiply the 5k. So that at the end we are going to get 12i plus 16j plus 20k. This is very simple and I hope you do understand. In case there are negatives inside, you just bring the negatives in and that's all. Let's look at the other aspect of it where we multiply vector and a what? And a vector. So in the multiplication of a vector, there are two. That is the scalar product and the vector product, or the dot product and the cross product. So in case we have two vectors A and B and we are finding the dot between them, the dot product between them is always equal to AB cos theta, where the theta here is the angle between the two vectors. Let's look at some properties of or the law that we have to obey in using the dot product. Anytime I is multiplied by a different direction, say j, say k, or say I is multiplied by what? A k, we always get what? 0, because in finding for the direction between them, it's always, let's say we have its magnitude to be 1, 1. We are going to have 1, 1 multiplying what? Sine 90 degrees, which is at the end going to give us what? 0. On the other hand, in case two of the directions are multiplying, so we have a unit vector with a direction I multiplying jj multiplying kk multiplying, we can get what? 1. And this law, you have to take very note of it because that is what you'll be using throughout. So let's try an example here. In case we are having a vector A that has its direction as ijk, so that we have axi plus ayj plus azk, and B is also what? bxi plus byj plus bzk, and we want to find the dot product between A and B, that's A dot B. This time around, in case we multiply I and I, we are going to get 1, so we can do that. But I and j is going to give us 0. I and k is going to give us 0. And j and k is also going to give us 0. So the best possible way of doing this is just multiplying the I, jj, and the kk, so that we get ax or can multiply bx, and ay can multiply by, and az can multiply bz. So that at the end, in case you have 2 here, they can multiply itself, and the I that we are having here will multiply itself, and from the rule we'll get 1. Likewise for the j and likewise for the k. Let's look at a vector product or a cross product. We define a cross product as, say we have vector A and B and we want to find a cross product between them for a third vector C, then it's going to be A cross what? B equals what? C. And C is perpendicular to the plane containing what? A and B. And it's defined as A cross B equals what? AB sine of theta, where the theta here is the angle, the small angle between A and B.